Think about the last time you washed a ceramic mug. It's a brainless task. You pick up the mug, turn it over, adjust the pressure of your finger so it doesn't slip, turn on the water, and scrub. If the mug is wet, you naturally squeeze a little harder to compensate for the slipperiness. If you drop the sponge, you bend down, pick it up, and adjust. But to a computer scientist, what you just did is a miracle of physics, coordination, and real time adaptation. For the last 50 years, if we wanted a robot to wash a mug, we had to write thousands of lines of precise mathematical code. We had to program the exact coordinate of the sink, the precise force the metallic claws should apply, and the exact path the arm should follow. If the mug was shifted just 2 inches to the left or replaced with a slightly different paper cup, the robot would crash, squeeze too hard, or miss the cup entirely. Robots were fast and incredibly strong, but they were completely blind, rigid, and fragile. But over the past year, you might have noticed videos of humanoid robots performing tasks that look almost shockingly human, folding laundry, sorting apples, or picking up fragile eggs without breaking them. Changed. It wasn't a breakthrough in metal gears or battery life, it was a complete paradigm shift in how we write the software brains of machines. Hi guys, welcome to Arya Nova. I'm Arya and today I want to take you past the flashy viral robot videos and look at the real software engineering that is bringing AI out of our screens and into the physical world. We are going to break down how generalist physical AI works, the mechanics of vision language action models, and how we are finally giving machines physical intuition. To understand the breakthrough, we have to look at how we used to build robots versus how we do it today. Historically, robotics was treated as a geometry and control problem. A robot had cameras that took in an image, software calculated the 3D coordinates of objects in space, then a trajectory planner solved complex physics equations to figure out how to rotate the motors in the joints to reach those coordinates. This is called a modular rule-based system. It works perfectly inside a highly structured factory where a car chassis is always in the exact same spot down to the millimeter, but it fails completely in the messy, unpredictable real world. Physical AI throws out this step-by-step math entirely. Instead, it uses a single end-to-end neural network. The core technology behind this is called a Vision Language Action Model or VLM. You are already familiar with large language models that take in text and output text. And you have seen multimodal models that take in text and images to describe what they see. A VLAM takes this one massive step further. It takes in visual images of the environment, passes natural language instructions, and outputs actions. Are the raw numerical forces and joint angles sent directly to the robot's motors. Think of it as a direct pipeline. Pixels in, actions out. How does a neural network learn to do this? It doesn't learn through programming, it learns through a combination of two methods, imitation learning and reinforcement learning. In imitation learning, a human operator wears a VR headset or uses a specialized rig to physically control the robot. The robot's cameras record the visual pixels and its sensors record the exact physical forces the human is applying to the controls. By repeating a task like folding a shirt hundreds of times with different shirts, colors, and lighting, the neural network learns the underlying correlation. It realizes when the pixels of the fabric look crumpled like this, the corresponding motor action should be to pull here. Once the model has a basic understanding, it transitions to reinforcement learning. The robot is placed in a simulation or a physical playground and allowed to try the task millions of times on its own. When it succeeds, the network is rewarded, strengthening those digital pathways. When it fails, it adjusts its parameters. Because the model is trained on diverse data, it develops something traditional robots never had: generalization. Generalization is the ability to apply learned skills to completely new situations. With a VLAM brain, if you show a robot a type of toy it has never seen before and say, "Put the yellow toy in the box," the robot doesn't freeze. It uses its vision model to identify which object is yellow, uses its language model to understand the word put, and uses its physical action model to estimate how heavy the object is and how to grip. It has learned the concept of tidying up, not just a set up pre-programmed coordinates. But this software shift has sparked a massive debate among computer scientists and roboticists. For decades, the industry relied on deterministic, rule-based code because it was entirely predictable. If a robotic arm on an assembly line malfunctioned, engineers could inspect the code, find the mathematical error, and fix it. With end-to-end neural networks, the robot's behavior is probabilistic. The decision making is happening inside a complex, multi-billion parameter black box. If a household robot drops a plate, you can't easily point to a single line of code to explain why. The industry is currently working on hybrid architectures containing the safety and boundary constraints of classical physics programming with the adaptive, fluid intelligence of VLAMs. When I look at this transition, I realize we are witnessing a quite historical pivot. For years, we have kept our computers locked behind glass screens. We have interacted with them through keys, clicks, and voice prompts. But physical AI is breaking that barrier. We are moving into a world where digital intelligence is gaining a physical presence, learning to navigate the gravity, friction, and chaos of our three-dimensional reality. And as these models scale, the robots around us will transition from programmed industrial appliances into intelligent helpers that can adapt, learn, and assist in our daily lives. I'm incredibly curious about how you feel about this as robots step out of the factories and into our daily physical environments. Does it make you feel optimistic about the chores they can handle, or do you have reservations about safety and control? Let's discuss it in the comments below. I'm Arya, and thank you for exploring this corner of the future with me here on Arya Nova. I'll see you in our next deep dive.